He will be talking on NASA hydrology satellite observations of the terrestrial water cycle. JT is a research scientist in surface hydrology group at Earth Science section at NASA Jet Propulsion Lab, or JPL. He studies Earth's water cycle with a particular focus on hydrologic extremes, sea level rise, and water resources. So without further ado, Dr. Rieger.
Thanks, Tom. Good afternoon, everyone. Can you hear me in the back? Sounds good? Okay. My name is JT Rager. I'm from NASA's Jet Propulsion Lab, and today I'm going to be talking about a NASA satellite mission called GRACE, which is a very unique mission. It's used to monitor the terrestrial and global hydrologic cycles, how water moves around the planet. I'll get into more details in a minute. How many people have seen the movie The Martian? Right? Very good movie, big Hollywood. Matt Damon, I think it won an Academy Award or something. I'm not quite sure. I don't know. But anyway, portions of this film take place at NASA's Jet Propulsion Lab. So a lot of people think about NASA activities, and they think about outer space. They think about sending humans to outer space. They think about sending rockets to other planets. They think about this type of activity. But about half of what NASA does is study the Earth, the planet that we live on, right? So we're sending satellites and other monitoring equipment to space to look back down at the Earth and understand how our planet is changing in time. We currently have 17 missions in orbit, Earth-observing missions in orbit around the Earth. And these are providing dynamic content, dynamic information on how the Earth is changing in time, how variable it is. And at this point in history, we probably have more data on how the Earth functions, more observations on the Earth than we've ever had at any point in human history. So think about that. Now we have the opportunity to understand things better than we've understood them before. So today I'm really going to be talking about water, water resources, the importance of water. We're here at COP-22 to talk about climate change. But of course, a big component of that is water. And water is a necessary ingredient for life, right? So when planetary scientists, astronomers, when they're looking for signs of life on other planets, the first thing they look for is a spectral signature of water, that a planet contains water. Because as we understand it, water is a necessary building block for life. So we live on Earth. Some people call Earth the blue planet. Of course, everything that you see in this picture that is blue is water, but everything that you see in this picture that's white is water as well, right? So our planet is really defined by water. Life on our planet is defined by water. About 98% of the water on this planet is in the oceans, and it resides there. About 1.6% of the water on this planet is in the ice sheets. That's the polar ice sheets, so Greenland and Antarctica. And only about 0.4 of the water on this planet is stored as fresh water on land. Most of that is stored as groundwater. So when we think about the little variability that can happen in the global water cycle, it can have big effects on how water is delivered to the continents and on our water resources. The water cycle is very dynamic. It's not static at all. Water evaporates from the ocean. It moves over land. It rains down as snow or liquid precipitation. And then it runs down, infiltrates the ground in some cases, evaporates through plant activity, transpiration, or runs back into the ocean, completing a circle that we call the global water cycle. And small changes in that evaporation over the ocean or in the state of snow over the mountains, small variations in these things can have big impacts on water resources. Water plays a role in all of our lives. So I asked this the other day when I gave this talk, how many people in here believe in water? Are there any water deniers in the audience? Right? How many people in here shower? Raise your hand. All right. How many of you drink water? Okay, so you guys all know water. You use it. I mean, water serves recreational purposes, serves health purposes. 80% of the water used in the world, consumption of water is for agriculture. So water supports our life, our food, and it's very important. Okay, so this is a bit of a science result here. What I'm showing is available blue water on this plot on the left. So this is the average global runoff, river runoff around the world, right? So this is the water, precipitation, it infiltrates, it doesn't evaporate, it runs back to the ocean. Where you see blue means it's a generally wetter place. So soils there are wetter, there's more runoff generation, and potentially more natural water resources in these places. Now, if you just contrast this map with the 2011 global map of our population density in the world. The places where you see red are more densely populated, and the places where you see green to blue to white are less densely populated. So contrasting these two maps, you have to ask, are we living where most of our water resources are? And very simply, by dividing these two things, we can get a per capita water availability, right? So we just divide those two fields, and we get something like this. Let's look at this distribution first. Most places in the world kind of fall into this middle range, right? So there's a certain amount of water per person in most places of the world. They don't really have water problems. If we look at the really wet places in the world, well, it turns out most people don't live in those places. So we think about the deep Amazon. You know, it's so dense, it's so wet that there's actually challenges to build infrastructure there, to have society there. And then we look at the lower 25th percentile of this graph, and we see a lot of places where we're just pushing the limits. There's barely enough water there for people to live, and water resources get really stressed. They get really stretched out. So Southern California is one of those places, and all of the places that are exceeding, these are the places that are in that lower 25th percentile, where water stress is important, becomes a part of everyday life, are shown in this map in the red and yellow areas. And so if we wanted to say, you know, by how much are these places exceeding some kind of a hydrologic carrying capacity, or how different are these places from the average, global average water per person, we start to get into these numbers of maybe Los Angeles has about, you know, 2 million people too many, maybe Mexico City has about 2 million people too many, New Delhi, Shanghai. Globally, about 2 million people are probably not in an optimal location where there's naturally water available, and as such, these people can experience water stress. That is an issue that these people are going to have to deal with. That's a large percentage of the population. Okay. So when we think about how the Earth works, we think some places, you know, they're just really dry, and some places they're just really wet, and it's always been that way, right? And it's never going to change, right? No, of course not. It has not always been that way. So when we think back about 10,000 years ago, portions of North America were covered in an ice sheet. The Earth was a very different place. New York City was under a kilometer of ice, right? So the election would have never happened because certain areas, right, they're covered in ice. Okay, and about 6,000 years ago, even the Sahara was a much greener place. So we know that now by studies of dust in the Atlantic Ocean and by studies of fossil plant material in the Sahara, that about 6,000 years ago, the Sahara was much wetter. It was more of a grassland, and people has moved from about 10,000 years ago, it was much drier. But during that 6,000 years ago period, people migrated out into the Sahara, developed communities there, and were able to survive there because there was much more water. So the water resources of the planet, they're not just static, they're really changing, they're dynamic in time, and that's the message I want you guys to get. They were dynamic in the past, they're going to change again in the future. So these are some of the IPCC projections for these different scenarios. We know that the planet is warming, and we expect that it will continue warming in the future. With changes in atmospheric temperature and land temperatures comes changes in the delivery of water to the continents, right? So a warmer atmosphere can theoretically hold more water. So you could have more evaporation, and you could have more precipitation in wet areas, but dry areas, they're just going to get hotter and there's no water there, they're probably going to get drier. When we see the patterns of global warming for different growth scenarios, we can notice like high latitudes are going to get them more warming, and that's been true what we see so far in observations. But also precipitation patterns are going to change. So these are projected changes in precipitation by the end of the 21st century. Where you see blue on this map are areas that should be getting more precipitation in the next 100 years. And where you see brown on this map are areas that should be getting less precipitation in the next 100 years. I live in California. Unfortunately, that's one of those places that is going to be getting less precipitation. And if you think back to that map that I showed of population and already water-stressed regions, several of those regions will be getting even more water-stressed even if we held population growth constant. So combining these two factors of climate change and population growth, we're going to have some real issues in the next 100 years of dealing with water stress. That's just something I want to bring your attention to. Okay, so I'm a hydrologist. That means I study water. I look at satellite data to do that. People use models to do that, or they use in situ data to go out and measure stream flow, things like this. I'm going to talk a bit today about the science of hydrology and why it's challenging. Hydrology is important. We know water moves around the planet. It's important to know how this is changing in time. Water creates the conditions for and limits life on land. It redistributes energy. Water is really responsible for moderate climates. You have more evapotranspiration. It cools things down. And water, they say hydrology is easy because water flows downhill, right? So if it rains at high altitude, water should just flow downhill. What's the science there? It's not so hard. I'll tell you why it's hard in a minute. As hydrologists, we're trying to close this budget all the time. So we have a certain amount of precipitation, a certain amount of evaporation, and a certain amount of river runoff in a region, and those all cause changes in the amount of water stored in that region. So trying to track these things in time, that's really our goal as hydrologists. Hydrology is hard because it's hard to get measurements of those fluxes and those stores, right? So there's not many observations globally. The primary means to measure river runoff is to put a stream gauge in the middle of a river. But if you think of a river like the Lena River, where this alluvial fan formation here, where do you put the stream gauge in this river? It's quite complicated, right? So it's not so easy. And if you're thinking maybe I'll just go upstream and put the gauge there, you can do that, but then you miss some downstream tributaries and you may not get a full measure of the amount of water flowing out of that river. To measure soil moisture globally, it would take millions and millions of people going out every single day to measure soil moisture globally because it changes so fast. Every time it rains in a place, the soil moisture changes. There's real challenges here. And finally, one of the biggest challenges is that a lot of hydrology happens underground. So water tables move up and down, groundwater is being pumped and depleted, and it's really hard to see beneath the land surface. You have to have money to dig wells. You have to have money to access water resources beneath the land surface. So that's why hydrology is hard. And in some ways, remote sensing is the perfect tool for hydrology because we can get that global coverage from space. We can see big events from space, like this Hurricane Matthew that struck Haiti in 2016. We can see those big events because we have that big eye, that big vision of how things are changing around the world simultaneously. This is another example of how hard it is to do hydrology. So this is from a recent research paper. Here we've taken a bunch of estimates of how much water is coming out of all the rivers in the world, right? And that's over the period from 1995 through the present. Using about 1 to 8 different estimates, we get 8 different answers for how much water flows through global rivers. It's just something that's not really well constrained. Most rivers don't have stream gauges. Think about rivers in the Congo, the Amazon, even the Mississippi, some of the biggest rivers, they can lose their stream gauges. It's hard to maintain stream gauges. It costs a lot of money, and it takes manpower to go out there and maintain those gauges and make sure they're still working. So we don't have a good idea even of how much water flows out of our rivers. Groundwater is a big issue, as I just alluded to a minute ago. Groundwater accounts for 96% of the unfrozen freshwater globally. That's 0.4. Most of that is groundwater. It's the major source of water for over 2 billion people globally, and it supplies roughly 45% of the water for irrigation globally. What happens if we run out of groundwater? Big problems all over the place. Groundwater supplies over half the drinking water, even in the United States, and about 60% of the water used for irrigation in the United States. But think about it, groundwater is the strategic reserve in times of drought, in times of dryness. So let's say you're a farmer and you use some surface water, you use some river water to irrigate your crops. But you also have access to groundwater beneath the land. If there's a drought, if the amount of water coming in the river decreases by any amount, and you want to maintain, you want to keep the same agricultural plan that you've got going on, it's very easy to turn to groundwater. So you just dig a well. If you can reach that groundwater, you're going to use it. So in times of drought, we tend to overconsume groundwater, and that's a major problem globally. This is just a depiction, of how groundwater kind of works. If you have a valley like this one, you can have snow, rain falling on these mountains. It'll trickle in and replenish an aquifer underground to provide groundwater. As humans, build farms and dig into that groundwater. We dig these wells. We're all putting a straw in the milkshake, so to speak, and we're sucking that groundwater out. Just because you're on your own farm using your own groundwater doesn't mean that you're not affecting everyone else around you. So groundwater is really a shared resource. And because we don't have access to many wells around the world, we don't have good well monitoring, it's really hard to track groundwater changes globally and to see how they're evolving in time. This is just a map from a recent paper by Tom Gleason that was in Nature, and it shows some big aquifers around the world. The places that you see that are colored in red, they're really exceeding their aquifer withdrawal capacity, right? So these are not sustainable aquifers. That means that what they've done here is they've done a little trick. So they've taken this aquifer, like let's take this aquifer in Saudi Arabia here, and they've said, how big would that aquifer need to be in order to sustain the current rates of withdrawal that are happening in that aquifer? So we see the actual aquifer shape in color there on the bottom, in red, And then we see the potential aquifer size scaled up that would be required to maintain the current rates of withdrawal. So as you can see, many of the world's biggest aquifers, they're currently not sustainable. So monitoring these global water resources is hard, and remote sensing provides a tool to get global coverage and provides a way forward for us to keep monitoring global water resources and how they're changing. The problem with remote sensing is that most remote sensing technologies are shooting something down at the ground, or they're taking a picture of the ground, something's reflecting from the ground. Most remote sensing technologies are using the electromagnetic spectrum, something in here, either visible light or microwaves, radar, something like that. And what they're doing is they're sensing energy return from the ground. This limits the perception of remote sensing observations usually to the top layer of the Earth or to several centimeters of the top layer of the Earth. We really don't see anything at depth using traditional remote sensing technologies. Okay, so now I'm going to start talking about the GRACE mission, the NASA GRACE mission, which is a totally different type of remote sensing technology. But in order to do that first, I want to give a little bit of a review of gravity. Gravity is a fundamental force in the universe. Let's talk a minute about how it works. Maybe you're going to remember some of this stuff from your physics class. So there's the complicated version of gravity, right, which is Stephen Hawking and Albert Einstein and space-time continuums. You don't have to understand that. Don't worry about that. The simple version of gravity is that if something has more mass, it tends to weigh more. And that's the situation we're dealing with. Something with more mass, it tends to weigh more, right? That's what we want to think about. Okay. This is the law of universal gravitation. It says that the force of gravity between any two objects is controlled by the mass of those two objects. So we have mass 1 and mass 2 here, and by the square of the distance between them. That means that there's a force of gravity between everyone around you right now. So you and the person you're sitting next to in the audience, there's a gravitational attraction between the two of you. Because your masses are relatively small compared to the mass of the Earth, which is huge, you're not sensing that gravity. But if you had infinite mass, or if you could get infinitely close together, you would actually feel that pull of gravity between the two of you. Yeah, so this is the Earth. The Earth is a massive, big chunk of rock, right? It's really heavy. And so the force of gravity acts through the center of mass of the Earth. Because the Earth is not a perfect sphere, it's rotating and it's experiencing the gravitational attraction of the moon, the Earth is more of a kind of football shape. You know, it's kind of oblong on the sides like this. It's not a perfect sphere. So the distance, remember distance is in that equation, the distance to the center of the mass of the Earth changes depending where you are on the Earth, right? So if I'm going to be in English units now, but if you're on the North Pole and you weigh 200 pounds and you walk down to the equator, you would only weigh about 198 pounds because that distance to the center of mass of the Earth has actually changed. So your weight would actually change. The pull of gravity would actually change in those places. So for me, this is yet another reason to move to the tropics, right? I can finally lose that last 2 pounds. Okay, just joking. Okay. So I just want you to understand that gravity is different in different places of the Earth. Gravity is a spatially variable quality, right? So it's different in different places. There's also local effects of gravity. So wherever you're standing on the Earth, right where you're standing, if there's a lot of mass right where you're standing, there can be a local augmentation of the Earth's gravity in that place. So if you're standing on a place that has really dense rock and crust, like a big mountain range, the gravity there will be relatively stronger than if you're in a place that's really flat with thin crust, like a desert or an oceanic plate. So on place to place, on the surface of the Earth, gravity is actually changing. And that gravity can be mapped in time. So this is a map of the Earth's gravity field, spatially variable. This is the static gravity field, the gravity field that we assume does not change in time. This is very important to calculate, for instance, the orbits of satellites, right? We need to know how the gravity field is spatially variable. We put something in orbit, but the pull on that satellite is going to change a bit as that satellite orbits the Earth. Where you see red in this picture, gravity is a little bit stronger. Where you see blue in this picture, it means gravity is a little bit weaker. There's still the mean gravity of the Earth, but there's variability around that mean. So for instance, the Andes Mountains, big, dense rock and crust. The gravity there is a little bit stronger than it is, for instance, in the Atlantic here, where we have this oceanic plate, and the gravity there is a little bit weaker. Okay, so all I want you to take out of this is that gravity can change in space, okay? Does that make sense so far? You guys with me? All right. Now I'm going to get into the actual GRACE satellite mission. GRACE is a joint project. It's an international project between NASA and the German Space Agency. So they've collaborated to make this thing work. GRACE has been in the news a lot. We've had some real successes in science with the GRACE data. NASA satellites can detect unexpected ice loss. They give a changing view of Earth's gravitational forces, the gravitational field, and how it evolves in time. Satellite flood prediction, so GRACE has actually been used to show when areas are saturated, they're getting really wet, and there's more mass there. And NASA satellites unlock secret to northern India's vanishing water. We've been able to monitor groundwater around the world. So I'm going to use the next few minutes to explain exactly how that works. These are the actual satellites as they were being constructed in Germany right before launch. Okay? So you can see from this picture that the satellites are about the size of a Volkswagen Beetle, something like that. There's instruments inside, batteries, things like this. But most importantly, on each face of the satellites is a microwave transmitter and a microwave receiver. We call it a microwave ranging device. So this side of the satellite shoots out a microwave emission, and it has a microwave receiver. And this side of this satellite shoots out a microwave emission and has a microwave receiver. So unless you didn't realize it already, this GRACE mission is not a single satellite, it's a pair of satellites. And they orbit the Earth in tandem. And here's what that looks like. So the satellites are in a polar orbit. That means they're going around near the poles. And as Ali explained beautifully the other day, it's not that the satellites rotate around the Earth. The satellites are pretty static in their orbit. It's that the Earth rotates underneath the path of the satellites, right? The Earth is rotating. So we have the satellites spinning around the poles, and the Earth is rotating underneath the satellites at all times. That's how the satellites get global coverage of the Earth. Satellites have these little discs on top, which are GPS receivers, just like the GPS receiver in your car or your iPhone. So because the GPS satellites are in a much higher orbit, they can look down on the GRACE satellites and say where they were at any time as they flew. This is how the GRACE satellites respond to changes in the Earth's gravity field, okay? So the two satellites are flying along in their orbit. If they come to a gravitational anomaly, a place with higher gravity, like a big mountain range, let's say the Himalayas, there's lots of snow, lots of dense rock and crust, the first satellite will be perturbed a little bit in its orbit by this local mass effect. And remember, the closer you get to that mass, the stronger the effect. So they'll be pulled a little bit in their orbit, and the distance between the two satellites, which is measured with that microwave ranging instrument, is going to be increased a little bit. As the satellites progress forward in their orbit, now they're both feeling the pull of this gravitational anomaly, and the distance between the two satellites will be decreased a little bit. As they continue forward in their orbit, the front satellite escapes the pull of gravity of this local mass, while the back satellite still feels it, and the distance between the satellites increases again. So for a single mass anomaly like this one, the distance between the satellite increases and then decreases and then increases again. And as I said, GPS is used to map these changes in the distance between the satellites all over the world, and it creates a global gravity field. This is what the planet actually looks like to these satellites. So this is an example of one of the GRACE solutions, the monthly GRACE solutions. Where you see red on this image means that there's relatively stronger gravity, and where you see blue means that there's relatively weaker gravity. The amazing thing about the GRACE satellites is that they're constantly flying, right? So we're able to do these gravity solutions every month. And every month we're able to see if the gravity field of the Earth is changing a little bit. The thing about gravity is how could it change, right? How could it change in time? There's one thing on this planet that is heavy enough and moves fast enough to really make a difference in the Earth's gravity field. Any ideas what that thing is? Water, of course. Water is really big and really heavy, and places get a lot of rain, and it can really change the gravity field. So in order to say, how do we get spatial change, temporal changes in the gravity field, what we'll do is we'll take the gravity solution for a given month, for example, September 2010, and we'll subtract from that the gravity solution for the long-term average, the static gravity field, the gravity we think is not changing in time. That difference makes a map of what we consider anomalies, gravitational anomalies. For GRACE, they're called global terrestrial water storage anomalies, with the assumption that most of those anomalies are caused by water. This is an example result. So this is one of the first results that came out of the GRACE mission in 2004, a nice science paper that shows the rainy season in the Amazon, okay? So wherever you see red on this map means gravity is relatively and temporarily stronger than normal. And wherever you see blue on this map, it means that gravity is relatively weaker and temporarily weaker than normal. And all we're seeing here is the rainy season. So you have average conditions in the Amazon right around here, but during the rainy season, we're getting really, really wet. And then that water actually, you can see it actually coalesces around the river system as it flows out back into the ocean. And then we enter the dry season in the Amazon through these months. And we're just seeing here a normal annual cycle of precipitation in the Amazon. So much water that it actually changes the Earth's gravity field. Okay. So these satellites, they fly over a region, they notice these changes in water mass. They don't really know what that change is coming from. They don't understand the source of that change. Is the change coming because snow underneath the satellites is melting? Is it coming because there's changes in lakes and rivers or soil moisture? Or is it coming because there's changes in groundwater? So for example, this is the Colorado River Basin, total water storage over a portion of the GRACE record. In the Colorado River Basin, we have big lakes and reservoirs that contribute to the water storage changes there. But soil moisture and groundwater are primary contributors as well. So in order to isolate one of those things, you have to know something about the other variables. And that's how we do groundwater with GRACE. Okay, so that's the overview of the GRACE mission. Now I'm going to just show you some highlights of the research that's been done with the GRACE mission since it launched in monitoring Earth's water. Eric, can we switch to the Greenland animation on the hyperwall? So we're going to jump into the hyperwall for a second because this is much more exciting than slides we've been looking at. Okay, these are GRACE results for the Greenland ice sheet, right? So you think you've got this telescope to see where mass is changing on the Earth. Where would you point this thing? Some of the first big results that came out of the GRACE mission were in monitoring the ice sheets. So towards the North Pole, we have this ice sheet in Greenland. And we know that with global warming, that ice sheet mass is changing in time. We can see that there's a strong seasonal cycle in Greenland. So every winter, when it snows a little bit, we accumulate a little bit of mass in Greenland. But every summer, when it melts, we lose a little bit more than we gain. So over the long term, we see this nice, steady decline in Greenland mass. And when I say nice, I don't mean nice. Okay. So the spatial distribution of that mass change is shown in the pink and blue here. Where you see red, it means it's losing the most mass. Can we do Antarctica as well? Thanks, Eric. Similar story for the South Pole, right? So the Antarctic ice sheet, really huge. The big worry is that a piece of this thing can break off and really affect sea level regionally around the world. So we've seen the mass change from GRACE. There's a lot less of an annual signal in Antarctica. It's not such a smooth up and down every year. But what we do see are these kind of big drop events. And I think there's going to become one coming up here, right, 2010 or 2011. And boom, there you go. So you get those big drops in mass that happen really fast from one month to the next. And that's because that's the nature of ice dynamics. When you lose ice, sometimes you lose a big chunk, and that causes big problems for sea level rise. Most of the mass change in Antarctica is happening here on the West Antarctic ice shelf. Okay, I'm going to go back to the PowerPoint now. Thanks, Eric. Just give it a second to load up here. So for hydrology, right, that's what we're talking about. For water resources, it's really the same technology. We're looking at the mass changes all over the world, and we're trying to understand what's happening there with water resources. A lot of places, I'm not going to say most, but a lot of places in the world have a rainy season. That means they have a strong annual cycle of wet and then dry, wet and then dry, wet and then dry. And that annual cycle really dominates the variability. So the Amazon, for instance, big annual cycle. But a lot of places also exhibit a trend over the GRACE record. And these are really short time series, but just to give you a taste, you know, the high latitudes here, the Lena Basin, you see a steady increase. And for instance, over here in Australia, during a period of drought, you saw a steady decrease in the mass. So using these time series from GRACE, we can say something about how water resources are changing around the world, how water storage is changing around the world. This is the GRACE trend map through 2014. So this is 11 years of data. These are the conclusions we've kind of had from the GRACE mission. The big things that pop out right away, of course, are the ice changes. Those are the really biggest mass changes around the world. So I'm not only talking about Greenland and Antarctica ice sheets, I'm also talking about Patagonia glaciers melting, Alaska glaciers melting, glaciers around the world. But we do see water on here. We see groundwater depletion in California, drought in Texas. We see La Plata Basin drought that occurred during the record. We see Middle East groundwater use and Australian drought. We don't only see drying, we also see wetting periods, right? So that's the interesting thing. Orinoco floods here that really tip things up increase the storage towards the end of the GRACE record. And strengthening India monsoon, which in some places has just led to more water storage in those regions. Okay, this is an animation. I'll just go with it. This is an animation, sorry for the low quality, of the GRACE changes over California. So in California, we've been experiencing a drought of epic proportions, really bad drought since about 2012. 2011 was actually a relatively wet year. You see the red here as we move towards the end of the record. Yep, so right after 2011, we had a relatively wet year. This is through 2014. 2015 and 2016, I don't have the updated slides, but they just unfortunately kept dropping and dropping and dropping. We're facing a real crisis in California with groundwater use during drought and water management. So this is a way that we could use the GRACE data to actually characterize the extent of drought. So we have the actual GRACE observations, up and down, all this stuff every year. We use what's called a climatology, which characterizes the typical up and down in a typical year, right? And we remove the average from that thing. Whenever we're beneath the typical up and down for a typical year, we consider that a departure from normal, or we call that a drought, right? Using the GRACE satellites, we can actually measure how far we are at any time from that drought event. So for instance, here from 2007 to about 2011, we had a little bit of a drought period in California. We saw the drought beginning, the drought ending, and right in the middle of the drought, the worst period there, we could measure what was the actual deficit in water stored beneath the surface. In other words, how much water would we need to get back to normal? And then we can do really cool things like probabilistic rainfall prediction and say, how long might it take for us to recover from this drought? Before GRACE, there's no way to measure how much water is actually missing from underneath the ground. So this is the first means to actually do that. The peak total water storage deficit in California was about 42 cubic kilometers in 2014. It's really big. It's the size of one of our biggest reservoirs, Lake Mead in the United States. And this is groundwater depletion over the GRACE record, plus looking back comparing to well data back to 1962. So one of the ways that we validate the GRACE data, people always ask this question, how do you validate? This is gravity. How does this relate to water on the ground? One of the ways we validate the GRACE data is by comparing to well data. So this is a really good match that we've gotten with California's Central Valley. Well data over California show a constant decline in groundwater storage through 2000, and then here appended is the GRACE record in green. We have a really long record. And what we see in California is what we see in a lot of places in the world. We do get wet periods. So the periods here shown in blue are relatively wet periods. We have some El Nino activity, this type of thing, and we do gain a little bit of water storage. But during times of drought, as I explained earlier, what we tend to do is we tend to turn to that groundwater resource when we don't have surface water. So during times of drought, we just hit it really hard. We gain a little, and then we hit it really hard again. These dry and wet periods, during the dry periods, we just push it too hard, and we're using up most of our water resources in this location. So you've got to think, this thing can't go down forever, right? Sooner or later, you're gonna hit a bottom. Or a lot of times what happens with groundwater is, as you get about halfway through the aquifer, the water quality starts to get so bad with dissolved solids and sediments that it's really cost prohibitive to actually use that water for anything. Yeah, so we've had some big successes in science. We publish these papers in science. We're very proud of our achievements as scientists, but nobody reads these papers, and we know that. So that's why we do activities like this, to get out there and talk to people, talk to the public, and try to educate people about what's happening with the scientific findings that we have. Using the same techniques, we've been able to monitor groundwater changes around the world. So these are the 7 most threatened aquifers in the world, at least during the GRACE period. That's not a policy statement, that's a scientific statement, right? So what we're seeing is these are the 7 aquifers that are showing the fastest decline over the GRACE period. They include the Guarani Aquifer in Brazil and South America, the Southern Plains Aquifer in the US, and the Central Valley Aquifer in the US. We have 2 in the US, depleting really rapidly. Northwest India is depleting really rapidly. The Middle East region there, and the Canning Basin in Australia. Australia had some really tough times with drought, and they're losing groundwater fast. Okay. As I mentioned briefly earlier, gravity observations can also be used to help predict floods, right? So if you see an area and that area is blue, as we've shown on the color maps we've used here, means storage is higher than normal. Just think of a bucket, right? You're filling a bucket with a hose. That bucket has a finite capacity. As the bucket gets fuller and fuller and fuller, and you're still running water into the bucket with the hose, sooner or later it's got to overflow. With the GRACE data, we can see the amount of water in the bucket, right? So we can see when that bucket's getting full, and we can say, man, you've got a really big risk here. And we created a term we call flood potential with GRACE, where we're able to map globally what's the current flood potential at any time. If a big rainstorm comes in, you could have big problems. And this has been helping with flood prediction. Here we were able to historically predict this major flood in the Mississippi River Basin about 5 months in advance. We could see this flood potential getting really high. So that's an important early warning system. We're working with NOAA and hoping to enact this technology for operational purposes. GRACE and dryness, wetness, dryness can also be used to help predict fires, the potential for fires. So if we have a certain land cover type, let's say it's grasslands, we have a lot of vegetation, a lot of biomass there, and that vegetation is very dry, we can say even before the fire season begins that you've got an elevated risk of fire in these places. So this is kind of the current fire potential outlook that we use in the United States. And you can see how coarse this thing is. It just looks like a cartoon. We're able to do something with the GRACE data that actually looks much more like this, much more quantitative and much more spatially specific. And we're hoping that this is going to help with the allocation of pre-season fire resources. We want to make sure we have firefighters in the right places to be able to respond quickly when a fire comes. Also, and I think this is the final slide, we're able to use the GRACE data to really study the movement of water around the planet. Big scale changes in the global water cycle. This is a paper that came out earlier this year that shows that we've had, on the whole, gains in hydrology over the continents over the past decade or so. These gains in hydrology are probably just caused by natural variability, things like El Nino, La Nina, that type of variability. But what they've done is they've actually masked sea level a little bit. So if we think about the current contribution to sea level, we have an ocean mass change. Of course, the oceans are expanding as well. But the ocean mass change is caused primarily by losses from Greenland and Antarctic ice sheets, and then a bit of a term from net land water storage, which includes groundwater pumping. When we pump groundwater, it goes into the ocean, and this is causing a nice steady trend in sea level rise as well. So humans are directly contributing to sea level rise. But these changes in climate-driven hydrology have also been offsetting that sea level rise the past year. So we've been masking about 0.7 millimeters of sea level rise over the past decade, meaning that the sea level rise that we currently think is happening is probably worse than it is. And these changes in hydrology, they're probably going to reverse in the next decade just due to natural variability, and we're going to get a big bump in the rate of sea level rise. So this is really only, this type of global analysis really only possible with these GRACE satellites. They've been a big breakthrough for the way we think about how water moves around the planet and the way we're able to study that in time. Okay, so this is my last slide. You know, the Earth is changing. Climates and water supplies will change as well. Some places may already be nearing unsustainable levels of water stress. We know that. And continued pressures by population and climate change are just going to really exacerbate those effects. Globally, water resources are really tough to monitor, especially if your water resources exist beneath ground. How do you see them? How do you monitor them globally? How do you get access to well data globally? It's a big issue. NASA's GRACE mission provides a means to look beneath the land surface, so it does provide the means to monitor the world's water resources. So using this technology, hopefully in cooperation with local and in situ efforts, we can actually provide a way forward to monitor changes in global water resources, including changes in drought and flood potential. So that's it. I think I'm done, and I'll open up for questions now. Thank you.
Yes, let's thank JT. Any questions?
It's basically the fresh water on the land that we're mostly interested in, isn't it? And so if all the water tends to go back down to the sea because the way we're treating our aquifers by drawing out of them and also by not covering the ground so that the water runs off the top, so they're not able to replenish as fast as they used to be able to when there was a lot more soakage into the ground, would you end up with a net negative amount of water? In other words, could you go far below? I mean, everybody says to me when I say this, they say, oh, but the water never leaves the planet, as though that's fantastic, you know. But one thing is that I don't think they're missing the point that the fresh water on the land going back to the sea is as good as if it left the planet for us.
There we go. That's a great question. And you covered a lot of important ideas there in kind of a big question. Yeah, so a lot of the water that's available in aquifers, it's really old water. They call these fossil aquifers. So I showed that ice sheet over North America and talked about how climates have changed over timescales of 6 or 10,000 years or 20,000 years. A lot of the water that's in the world's aquifers today was put there 20,000 years ago when we had a much wetter climate in some places. And that water infiltrated through the soil and then stayed there in the aquifers. Now those places have become dry. People still want to live and grow crops in those places, then they're going to turn to the groundwater. So it's not that there's a net zero change in water on the planet. This is true, that we're not losing or gaining water, but it's the accessibility to that fresh water that really makes it a challenge. There was a second part to your question. I kind of forgot what it was, but does that answer? Okay, thanks.
Thank you very much. Very excellent presentation. We are working with the NCAR, National Center for Atmospheric Research, and also United States Forest Service on the watershed-based adaptation to climate change. So we are utilizing WEEP model, water evaluation and planning, and also include downscale modeling. We input all the factors that you are explaining to us. Have you ever compared these two technology between downscale modeling, WEEP model, and the satellite data utilizing GRACE technology? Have you ever compared the two kind of research?
So I'm familiar with the WEEP model, actually. So this is a big network model of different management structures and reservoirs and how they get managed in time. It's a highly parameterized model. It doesn't really deal with a lot of natural processes like underground water, right? So the big issue in many places is we don't know exactly how much water we have underground. There's really, it's impossible to measure that. We know how much we're taking out, but we don't know how much is there. It's really hard to see that. And we also don't know how the quality of that water will change in time. So GRACE is giving us an insight into that, and we know that what we see with GRACE, it does kind of match what we're seeing from use versus consumption to match that net rate. And that's just done, kind of back of the envelope type validation. But eventually we need to move towards, and this is for everyone, this is in a global climate model sense as well. I think eventually we need to move towards physical models of the planet that actually incorporate human processes, that incorporate human management decisions and human water management decisions. Because certainly things like agriculture, they're going to change land atmosphere communication, and they're going to change the climate regionally in places. So yeah, this is a very important next step in the future, is combining those types of models with physical models of physical understanding of the planet. Yeah, good question.
All right, JT, one over here.
Frank McGovern from Ireland. I may have missed this at the outset, but thanks for a really elegant presentation of what you're capable of doing with GRACE. But I'm interested just to find out a little bit more about the detail in terms of the temporal and spatial resolution that you can provide. So I suppose how localized can you provide this sort of analysis?
That's a great question. I didn't really get into that too much. Perfect question. So the temporal resolution is about 30 days. It takes about 30 days to get full coverage of the Earth, and we make one of these gravity fields. Spatial resolution is a little trickier. So the satellites fly over a region, and the satellites are not shooting anything down at the ground. So there's no footprint, so to speak. What they are is they're kind of dancing in orbit. They're feeling that pull on them from the ground. They don't know exactly where that pull is coming from beyond a certain radius, right? So they feel some change beneath them. They don't know if it's coming from this mountain here or this mountain right here as they fly over that path, but somewhere in that footprint. So the spatial resolution of the GRACE satellites is about 2 degrees by 2 degrees, latitude and longitude, or about 200 kilometers by 200 kilometers at the equator. That's a big scale. But it's kind of consistent with current global climate models. It does give us something we can say on big areas, how much are things changing. If there was a really high change, a big signal, smaller than that footprint, the satellites would see it. They just wouldn't be able to say exactly where in that footprint it's coming from. So there's a bit of that insensitivity spatially to be able to resolve an exact location of a signal. The work that we've been doing at NASA is to combine those GRACE observations with a model observation, or a model prior, we call it, Where if we have some prior knowledge on, well, here's a mountain range and here's a valley, this should be snow, that should be groundwater, then we can take that lumped GRACE signal and we can decompose it a little bit using data assimilation. So this kind of model-supported GRACE data is kind of the next frontier. That's something we're working on. The big demand from water managers, especially regional water managers, has been, you have to scale this data down to something that we can actually act on if we don't know what's happening in this big footprint. So it's something we're working on. Excellent question. And I hope in the next few years we're really going to be able to tune in that resolution. Great.
One question over here.
Hydrology model.
Thanks for the presentation. I'm working for the Remote Sensing Authority, at the head of Department of Natural Resources, monitoring and mapping natural resources. My question is, for the radar, if we use the longest wavelengths, does it work for monitoring the groundwater if we use also INS2 data? Work?
Okay, I'm not sure I understood the question. Can you say it again?
Yeah.
Sorry.
For radar data. Radar data.
Oh, radar. Yes. Okay. Right. Yeah.
And INS2 data.
Yeah.
This can help in
Yeah.
monitoring the groundwater.
Yes, that's a great question. So there's different wavelengths of radar. This is what the question about. There's different wavelengths of radar that can actually penetrate deeper into the ground. So right now, NASA's thinking about something that combines a P-band and an L-band radar, which would go much deeper. You would still only get maybe a meter or so into the ground. The thing is with radar, as soon as you hit any water, so you hit a water table, you're gonna bounce back. It's gonna hit that signal, and you're not gonna be able to go any deeper. So in order to see really deep aquifers using a radar technology, you would need a completely dry surface. So think about that. You would need essentially a desert surface, deep groundwater, where you shoot the radar down, and then it only comes back when it finally hits that water. Using really long wavelengths, we could go pretty deep, but there's not too many places in the world where that type of situation exists. So for global monitoring, we're really thinking about, all right, let's use gravity combined with something that gives us deep soil moisture, maybe like 1 meter, 2 meter deep, and then this combined technology could give us a real picture of the vertical water column, how water is distributed in depth all over the world. It's a great question. Yeah.
Hi, JT. Woo. Sorry. Hi, JT. In the back. One question here.
Hi, this is Mohammed Al-Meheri from National Center of Meteorology and Seismology in the United Arab Emirates. Thank you for the beautiful presentation. Just I have a very quick question. Have you considered cloud seeding as one of the solutions to solve the problem of fire problems or dryouts in US? Because I know that NCAR is doing it, but I don't know if NASA is working on it.
No, I'm not aware of any efforts on cloud seeding at NASA. No. Thank you. Yeah.
All right. Do we have any other questions? Well, I have one question. How do we verify GRACE? What are the efforts that you mentioned how there's not a lot of wells to take a look at? Do you look at wells? How do you make sure that what GRACE is saying is in some way grounded?
Yeah, that's a great question. So we do use well data when we have it to validate the GRACE measurements. That's pretty easy in countries that have good well data. A lot of places do not have great well data, or it's not openly accessible, so it can't be used. Luckily, we do have other NASA missions even that represent global precipitation. So like the TRIM mission and the GPM mission tell us how much it's raining all over the world. As long as we're getting a GRACE signal that essentially correlates with that precipitation, we have more accumulated precipitation, we see an increase in storage, and that the scale is appropriate there, we know that we're seeing something accurate. The other two loss terms, though, runoff and evapotranspiration, much harder to measure. Great question.
Hi, I'm Steven. I'm a researcher at Brown. My question is, do you ever use this data, whether in private sector or public sector, to put an economic value on this water, whether that's in insurance programs or just drought prevention or anything to that effect?
That's a brilliant idea. I would love to see something like that, but I'm not aware of anything at NASA that's approaching that. I think it might just be beyond our domain to some extent. But with the correct economic framework, evaluation framework, I think something like that would be worthwhile. Yeah.
All right. Here. Please introduce yourself.
Yes, Thank you. I'm Semia Harbi from Tunisia. At the moment in Tunisia, the resources in water becomes more and more. We suffer from the salinity and the quantity. So, if I understand very well what you have said, so if we say that we start suffering from the resources of water, so should we go and see if we have in ground some water and to look if we have some water in ground? As you said, we cannot we cannot yet count the water in ground. Thank you.
Yeah, so just to clarify, with the GRACE mission, we're only seeing changes in the Earth's gravity field, right? So if there were a big hidden aquifer somewhere and no one was using it, we wouldn't be able to see it. So we're only seeing, if it's actually changing in time, then we would be able to track it. We see that kind of net mass difference. But with the big static gravity field, the constant gravity around the Earth, we can't really say, nothing's changing in time. We don't know, why is the gravity field different in different places? Is it mountain? Is it ice? Is it water? Who knows? Yeah, so that's a tough one.
I have two questions. One is, does the salinity of the water vary the response of GRACE compared to fresh water? And the second question is actually more of a comment. There's a movie called Green Gold on the internet, which says that the plants, that the capillary action, if you shade the surface, draws the water right up, even in a desert. They've actually changed the Gobi Desert to make it green.
Yeah.
So is that what you understand to be, that every desert potentially has enough water underneath it, that if you just covered it in the way that you're meant to do to let the capillary action reach the surface, you would be able to grow something?
The second question first, I would say no. I would say that if it doesn't rain in a place, you're going to have problems getting a wetter climate. For the first question, yeah, the salinity of the water is really within the error bars of GRACE. So when you talk about salinity of ocean water, it's parts per thousand. It's not changing the density of water enough that we're able to really sense that with the GRACE measurements. Yeah. Any others?
Any other questions? I have one question. Will GRACE last forever?
That's a great question. So actually the GRACE mission is on its final days probably. We're in our 14th year of operation, which is a really long time for a NASA satellite. Fortunately, we have the GRACE follow-on mission, which is essentially an identical mission, and it's going to launch in 2017. So we're hoping for another 14 years of monitoring after that. That long record will be really important for tracking the ice sheets, tracking continuing changes in aquifers around the world. That type of continuity for NASA missions is also really important. Thanks.
All right, we have time for a couple more questions.
Yeah.
Hi, this is Mariam Al-Mazroui. I'm a project engineer at Masdar Corporate. So what you are doing is you are monitoring the water resources at the Earth, right? Is there any plan to go ahead and look to the solutions beside desalination? We have to look to other kind of solutions. Right. Is there any plan for that?
So as a scientist, from a research perspective, it's our job to kind of study the Earth, understand how it's working, understand how processes work, and management or policy decisions are not really in our scope of what we do at NASA. So there's no plans at NASA to do that type of optimization of irrigation or these types of management activities. Yeah, our job is essentially to report to the world what we see. So it's that tool. GRACE offers a tool for monitoring for water resources, and it's specifically that niche that we fill at NASA is that we're able to monitor how things are changing in time and better understand how that works.
Yeah. All right, question right here in the center.
Yes, thanks for the excellent presentation and answers. My name is Peter Bocek. I'm with the European chemical industry, and I was interested in your comment on the history 6,000 years ago where people were living in the Gobi Desert or in the Sahara, showing us that indeed there are dynamics and where people were living before, they are now not living anymore. And I think what you are doing is monitoring the development in a short period. But I think what you could not promise, what some politicians may try to promise, that we can sustain a certain status and then we can expect that this will remain the same forever. So I think there will be change and we can measure the change, but the extent to which we can prevent the change or change the change is very, very little, right?
Yeah, that's a good point. So just to clarify, those changes that we saw in the Sahara about 6,000 years ago, scientists understand that was mostly due to orbital changes in the Earth. So the tilt of the Earth was actually a little different, which caused a different distribution of precipitation and different climate in different places. Yeah, monitoring is an important tool, though. If you're thinking about management, if you want to inform management, monitoring is always the first step. If you have to know what you have in order to know how to deal best with what you have, right? So that's my comment there.
All right. Time for one more question. All right, if not, let's give Dr. J.T. Rager a round of applause. Thank you.